So picture this. If a strategic U.S. satellite suddenly just, goes dark today, historically, that's a massive problem. I mean, it takes years and hundreds of millions of dollars to replace it.
Oh, absolutely. It's a logistical nightmare. You have to secure funding, design the payload.
Right. Find a launch vehicle, wait for an actual launch window, and then basically cross your fingers that the weather holds out.
Exactly. It's a massive waiting game.
But what if you could replace a multi-million-dollar orbital asset before you even finish your workday?
Welcome to this deep dive.
Yeah.
Today, we're looking at a 16-hour sprint that just, well, made billion-dollar space blockades completely obsolete.
Yeah, it's a completely watershed moment for aerospace engineering.
We actually got our hands on a June 2026 press release detailing Rocket Lab's groundbreaking Victus Haze mission for the U.S. Space Force. And we're unpacking a fundamental shift in modern space defense. We're talking about a mission that went from a notice to launch order to actual literal liftoff in under 17 hours.
Which is just wild. Right. It fundamentally shatters our understanding of military space acquisition and orbital maneuvers. I mean, under 17 hours.
The sheer speed is absolutely the headline here, I agree. But, the engineering mechanisms that made that speed possible are what truly rewrite the rulebook.
How so?
Well, we're moving from a paradigm where space assets are these vulnerable, irreplaceable behemoths to an era of rapid tactical response. And while a fast rocket is impressive, the implications for space domain awareness, basically our ability to monitor and respond to threats in orbit, that's what permanently alters national security strategy.
Okay, to really grasp the magnitude of this achievement, we have to start the clock exactly when Rocket Lab received their orders. We're talking about the notice to launch.
Right.
This order came down from the Space Systems Command's Space Safari Program Office. And from the exact moment that order was received to the moment the Electron rocket lifted off the pad at Launch Complex 1 in New Zealand, the total elapsed time was exactly 16 hours and 42 minutes.
Which is a metric that is incredibly difficult to comprehend if you're familiar with traditional aerospace timelines.
Yeah, it sounds like sci-fi.
It really does. To give you some context, they were given a strict 24-hour deadline for this mission.
Which they obviously beat.
Completely crushed it. But more importantly, they completely shattered the previous tactically responsive space record, or TAC-RS as it's known, which was held by the Victus Nox mission. They beat that record by more than 10 hours.
10 hours? Shaving 10 hours off a rocket launch isn't just about, working faster. It requires a totally different approach to the math. And, okay, let's unpack this. I want to drill into that math. Specifically, the guidance, navigation, and control team, the GNC team.
Oh, yeah. The GMT turnaround on this is staggering.
The source notes, they calculated the final trajectories, updated the flight software, and aligned global ground stations in roughly 4 hours. How is that even physically possible?
Right, because traditional mission assurance reviews take weeks of people in conference rooms double-checking equations.
Exactly. It's like taking a spontaneous cross-country road trip where you only get the destination hours before leaving, but you have to perfectly calculate every single red light, road closure, and fuel stop in real time, except you're moving at 17,000 miles per hour.
That is a very accurate analogy. Doing this in 4 hours requires a complete departure from bespoke manual engineering. Normally, GNC is this meticulously deliberate process. You have to calculate the payload mass against atmospheric density.
The exact rotational velocity of the Earth at the time of launch, right?
Exactly. And the specific orbital insertion point. Doing all of that in 4 hours means you aren't doing the maths from scratch on a whiteboard.
So they're using what, like pre-calculated templates?
Essentially, yes. They utilize highly automated, pre-validated orbital shells. The software architecture is designed to accept final variables, like a last-minute orbital destination, and then instantly generate the trajectory.
Oh, wow.
Yeah, you don't achieve a 4-hour GNC turnaround by running down the hallway faster. You achieve it by bypassing the traditional human-in-the-loop bottlenecks.
So they're just trusting the software.
The software is trusted to make the calculations, update the flight profile, and coordinate the telemetry across their network of global ground stations, all while maintaining rigorous flight safety standards.
So the rocket gets off of the pad in 16 hours. But a fast launch doesn't actually help the Space Force if the satellite it drops off takes a month to boot up, unfold its panels, and calibrate its sensors.
Right. Getting to low Earth orbit is only half the battle.
Exactly. How did they solve the bottleneck once the payload actually reached space?
That brings us to the commissioning phase. Launching is just the delivery mechanism, right? Commissioning is when the spacecraft actually wakes up, runs its diagnostics, stabilizes itself, and becomes an operational tool.
And for the Victus Haze mission, the payload was the Pioneer spacecraft.
Correct. And Pioneer was fully activated, readied, and commissioned for its first orbital maneuver in 37 hours and 36 minutes.
And the deadline they were given for this phase was 72 hours. So they beat it by over 34 hours.
Exactly. But the critical part isn't just that it woke up quickly. It immediately began executing rendezvous and proximity operations.
RPO.
Right, RPO.
Yeah.
It was simulating a rapid threat response scenario where it had to chase down a non-compliant satellite to photograph it and monitor its behavior in real time.
Now, I have to push back on this a little bit because orbital physics is notoriously unforgiving.
No.
In space, you can't just, point your ship at a target and hit the gas like you would on a highway.
No.
If you fire your thrusters to speed up, your orbit actually widens, your altitude increases, and you slow down relative to the ground. Rendezvous is this highly counterintuitive dance of raising and lowering altitudes to catch up to an object. Doing the math for that and executing it safely in a day and a half without causing a high-speed collision that creates a massive cloud of debris that just seems incredibly risky.
What's fascinating here is that the ability to perform these rendezvous and proximity operations on such a compressed timeline relies on the exact same autonomous architecture we saw with the launch trajectory.
Right.
Yeah. Because orbital mechanics are so counterintuitive, the spacecraft has to make real-time decisions without waiting for human operators on the ground to double-check the math for every single maneuver.
But how does the spacecraft even know where it is? The source mentions components like star trackers and reaction wheels being critical here. Let's break down what those actually do for the listener.
Sure. So a star tracker is essentially a specialized camera. It maps the constellations around the satellite and compares them to an internal database.
Okay.
And that tells the spacecraft exactly how it's oriented in the pitch black of space.
Got it. And the reaction wheels?
Reaction wheels are these heavy spinning tops housed inside the chassis of the satellite. By changing how fast those individual wheels spin, the satellite uses that momentum to pivot, tilt, and aim its cameras or its thrusters without having to burn limited chemical propellant.
So it's basically constantly mapping the stars to find its footing and then spinning these internal wheels to swing around and face the target satellite.
Precisely. And the onboard flight software is calculating those complex orbital phasing burns you mentioned entirely autonomously.
That's incredible.
It is. That real-time agility is the absolute cornerstone of space domain awareness. If a hostile satellite does something suspicious, you can't afford to wait a month to get eyes on it. You need to launch, intercept, and observe before they complete their objective.
Which means the hardware and the software have to be in perfect sync to pull that off. And here's where it's really interesting. This brings us to the supply chain. Because according to the source material, a timeline this compressed isn't just about the thrust of the rocket, it's about the structure of the manufacturing.
Exactly.
Victus Haze marks the very first time that a single prime contractor provided an entire, space-as-a-service package. Rocket Lab designed it, built it, tested it, launched it, and is running the 247 on-orbit operations.
Which is huge, because the logistics of defense procurement are traditionally a massive bottleneck. When you have dozens of different contractors building different pieces of a spacecraft, you inevitably run into integration issues.
Think of traditional satellite manufacturing like trying to build a custom house, right? You rely on 50 different subcontractors.
Oh yeah, delays are inevitable.
Right, you're waiting on the plumber, but the electrician hasn't finished, and neither of them can work because the drywall guys are late. Contrast that with what Rocket Lab did here. It's like they built a fully functional modular home entirely in-house, eliminating all those third-party bottlenecks.
That is a very apt comparison. They completely eliminated the third-party interface friction.
Yeah.
The press release details their vertical integration strategy in depth.
What exactly did they build in-house?
The Pioneer spacecraft incorporates subsystems built entirely under one roof. We're talking about the propulsion, the solar arrays, the reaction wheels, the radios, the star trackers, the physical structures, the propellant tanks, and the flight software. Every single critical piece.
So the flight software speaks the exact same language as the star trackers from day one.
Yes, because the teams that design them are literally sitting in the same building. You don't have to wait for a vendor in another state to ship you a specialized fuel valve, only to find out it doesn't quite fit the physical interface of your propellant tank.
Which would then trigger, what, a 6-month engineering redesign?
Easily. This internal supply chain guarantees seamless compatibility between the rocket and the payload. And more importantly, it fundamentally shifts future military space acquisition strategies.
Meaning we are moving away from building these irreplaceable, bespoke, billion-dollar battleships that take 10 years to get off the ground.
And moving toward an agile fleet. The model shifts from massive, decade-long procurement cycles to having modular spacecraft sitting on a shelf, fully integrated, just waiting for a mission file to be uploaded.
So what does this all mean? Now that we understand the mechanics, the 16-hour sprint, the automated orbital math, the autonomous rendezvous, and the vertically integrated supply chain, we need to look at the geopolitical impact. How does this record-breaking speed fundamentally alter the landscape of national security?
Well, the release quotes U.S. Space Force Lieutenant Colonel Lincoln Miller, who is the Space Safari System Program Manager. He described Victus Haze as the culmination of the TACRS crawl, walk, run phase.
And it sounds like we are officially in the run phase now.
We definitely are. And Lieutenant Colonel Miller made a vital strategic point. He stated that demonstrating the ability to commission a complex space vehicle in under 72 hours and immediately begin rendezvous and proximity operations shows that the U.S. can field capabilities to deny adversaries a first-mover advantage into novel orbits.
Let's define what that means for national security. A first-mover advantage into novel orbits. Basically, if an adversary tries to sneak a satellite into an unexpected orbital path, maybe to spy on something new, or to gain a tactical edge over our communication networks, we don't have to just sit there and watch it happen for months while we build a response.
Right, we can launch our own asset to counter or observe it almost instantly. Space is an increasingly contested domain. It is a critical theater of operations now. The CEO of Rocket Lab, Sir Peter Beck, echoed this sentiment in the release. He stated that this launch plus spacecraft integrated capability is what modern space power looks like. It is the ability to reinforce and reimagine national security space architecture at will.
I mean, think about what this means for the concept of a secure orbit. For decades, if a satellite was compromised, whether by a solar flare, a stray piece of debris, or an intentional hostile act, it was a devastating loss. It left a blind spot in defense monitoring that could last for years. But now, if an adversary were to disable a satellite, we can theoretically replace it or deploy an observer before the debris even settles.
If we connect this to the bigger picture, this rapid response capability acts as a massive deterrent. In geopolitical strategy, deterrence is about convincing your opponent that any hostile action they take will be immediately countered, right? Basically rendering their original action useless.
So it takes away the element of surprise.
Exactly. If an adversary knows that you can replace a disabled satellite in 16 hours, the strategic value of them attacking that satellite drops to near zero. Why risk an international conflict to blind an opponent for less than a day? The speed of the response nullifies the impact of the attack.
It completely changes the risk-to-reward ratio for hostile actions in orbit. And Rocket Lab actually has the operational history to back this up, right? The source notes their extensive history of responsive space missions.
They do, yeah. Back in 2024, they set a previous record by launching 2 Electron missions from 2 completely different hemispheres in less than 24 hours.
Wow.
Yeah, they have been proving this rapid, reliable launch cadence over and over, and it's a cadence that the release dates is unmatched by any other small launch provider globally.
It's that consistency that makes this a true capability rather than just, a one-off experimental demonstration.
Right. When you combine their reliable launch cadence with extreme vertical integration and autonomous on-orbit commissioning, you transition into a robust operational defense architecture designed for immediate tactical response.
It is a complete overhaul of how we view our infrastructure in space. So let's bring all of this together and distill the key takeaways from this source material for you. We started with an order from the Space Safari Program Office. From that exact moment, it took 16 hours and 42 minutes to get the Electron rocket off the pad, completely crushing the 24-hour deadline and obliterating the previous TACRS record.
Yeah, and then we saw the guidance, navigation, and control team bypass weeks of manual reviews by utilizing highly automated, pre-calculated orbital math to finalize trajectories in a mere 4 hours.
Right. Then we watched the Pioneer spacecraft reach low Earth orbit, boot up, map the stars, and become fully commissioned in just 37 hours and 36 minutes, beating its 72-hour deadline by more than 34 hours.
And immediately executing autonomous, counterintuitive rendezvous maneuvers to chase down a target.
And we explored how this was all made possible by extreme vertical integration building, the propulsion, the solar arrays, and the software all within the exact same ecosystem, which basically transformed a multi-year defense procurement headache into a multi-hour tactical advantage.
It really is a stunning display of modern space power that denies any adversary the luxury of surprise.
But as we wrap up this deep dive, I want to leave you with something to mull over. We've explored the incredible engineering that makes this rapid response possible and the strategic deterrence this speed provides for national security. But if we can launch, deploy, and rendezvous this incredibly fast, what happens when space becomes just as dynamically contested as the airspace within our own atmosphere?
That's the real question.
Will this new reality of rapid response capability lead to a more secure orbital environment through mutual deterrence? Or could this sudden agility trigger an escalating game of rapid-fire orbital cat and mouse? A scenario where autonomous satellites are constantly chasing each other in low Earth orbit, an environment that we simply don't yet have the international laws and treaties to regulate.
It's definitely something we're going to have to figure out, and fast.
When the clock is ticking down from 16 hours, the engineering might be flawless, but the geopolitical consequences are just beginning to launch. Thank you so much for joining us for this deep dive. We'll be back next time to unpack more of the ideas shaping our world and our orbit. Keep looking up.